Você me avisa, né, Simone?
Aviso, tá? Vai entrar aqui no ar. No ar, né?
Tô?
Uhum.
Ok.
Tá.
Ok. Bom dia. Vamos continuar com a série de seminários, de webinários do Observatório Nacional. E hoje eu tenho o prazer de apresentar para vocês o Dr. Eric Miller, que vai falar para vocês sobre o satélite que está vindo em alguns anos no futuro de raio-x, chamado Chrism. Eric, ele terminou o doutorado na Universidade de Michigan em 2003, foi trabalhar no MIT em 2009 em diante. Ele virou Research Scientist, pesquisador no MIT. Ele fez uma significante número de contribuições em vários tópicos envolvidos com matéria difusa em galáxias, aglomerados de galáxias, espaço intergaláctico, e etc. E mais recentemente se voltou a fazer uma série de trabalhos em desenvolvimento de processamento de dados e data reduction para dados astronômicos e calibração e monitoramento dos instrumentos de raio-x. Ele é parte do grupo de trabalho científico do AstroAge, Hitomi, desde 2012. Faz parte do Consórcio Internacional Astronômico para a Calibração de Altas Energias e do Grupo de Trabalho Científico Suzaku desde 2005. Atualmente, ele é parte do grupo de ciência do Chrism, desse satélite, e também está liderando a calibração, o plano de calibração do satélite, e ele é como se chama, o PI, o investigador principal de um dos instrumentos, o Xtend, que é vai ser um monitor de alto campo no Chrism. Então, sem atrasar mais, então eu passo a palavra para Eric. Oh, Eric, I'm sorry, I spoke Portuguese the whole time, but basically you are introduced.
That's okay. I think I actually followed a lot of that. Although I should point out, I'm not the PI of Xtend. Is that what you said?
Yes, I said.
No, not quite. I'm the instrument scientist for the ground segment of Xtend.
Oh, okay.
I'm kind of the point of contact. Yeah, I do want to clear that up because I don't want to answer questions about Xtend pretending I'm the principal investigator. So, okay.
Okay.
All right. Okay. Great. So let me share my screen. And thank you for the wonderful introduction, some of which I understood. How do you usually handle questions? Do you just save them for the end, or do you want to stop halfway and see if there are any questions, Renato?
Yes, we save for the end all the questions, which are the attendees' questions and also questions from the YouTube.
Okay, great. Sounds good. Okay. All right. Well, thanks again for having me. It's a pleasure to join you and be able to talk about XRISM. So that's what I'm going to talk about today, the XRISM X-ray Observatory, which is currently being constructed for launch in a couple of years, and specifically how it will open a new window on galaxy cluster astrophysics. All right, so I do want to acknowledge the XRISM science team, which is shown here. This picture was taken back in October 2019 at the last science team meeting we had in person, which was in Japan. There are about 100 or 150 members of the science team for XRISM. The XRISM is a Japanese-led mission led by JAXA with important contributions from both NASA and ESA. And so the science team is really an international collaboration of scientists who have been working in this field, basically many of them since the time of Suzaku about 16 years ago. We've actually had 2 additional team meetings during the pandemic, all online. So the work is still ongoing despite the fact that most of us can't travel. Okay, so I'm going to spend a little bit of time talking about why we want to do X-ray spectroscopy and what we can learn from it. And then I'll move on to talking about what XRISM can do and introduce the instruments, and then finish up by talking about what Hitomi did for galaxy clusters and what we hope to do in galaxy cluster astrophysics with XRISM. All right. Okay, so I think most of the people on this call understand that astrophysics is really enabled by spectroscopy. So simply taking images of celestial objects allows us to do a lot of things. It allows us to do things like counting the objects, exploring their morphology, things like that. However, if you really want to understand the physical conditions of the objects that you're studying, you need to be able to measure the energies of the photons that you're receiving, since we can't go and take in situ measurements. The sorts of astrophysics that measuring photon energies reveals are things like what is producing the light, what kind of material is it, how hot is it in equilibrium, or is it in some transient state, is it moving around and how fast is it moving, what is its chemical composition, how far away is it, that's the sort of thing you can get from redshift information. And of course, what else lies along the line of sight, and what is that material doing? And so this information comes from a variety of spectral features, including the shape of the continuum, the presence and strength of emission lines, and the presence and strength of absorption features. So this isn't simply taking images. This is measuring photon energies, and the more precisely you can measure photon energies, the more information you receive about the astrophysics of the object under study. Okay, so just as kind of a simple example of this, specific to X-rays, this is an image of a supernova remnant. This is E0102, which is the brightest X-ray supernova remnant in the Small Magellanic Cloud. This was taken with the Chandra X-ray Observatory. And in fact, this image shows both the X-ray emission, which is this diffuse emission you see, along with optical emissions. So all of these stars here are in optical. But if you don't have information about the photons themselves in terms of their energy, then you can determine something about the supernova. And just simply looking at it, obviously you can tell it's round, it looks like a ring. So you can discern that it probably is the result of an explosion of a star, which was somewhere in the middle here. And you can see all of this filamentary structure. That's about it, however. So if you add in the information about the energies of different X-rays, you can do something like this. And this is just a very simple example. This is just taking the high energy X-rays and coloring them blue, and the low energy or soft X-rays and coloring them red. And right away, you see that there's a difference in the low energy X-rays and the high energy X-rays in space, which tells you, again, in the simple model, that the material on the outside of this supernova remnant is hotter than the material on the inside, likely because it's been recently shock heated by the passing shock front of the supernova. So in order to do this, you need to measure the photon energies. So another way you can view this, of course, is just to extract all of the X-rays in the remnant and plot them as a histogram, which is shown here. So this is just a spectrum of that supernova remnant. Now this X-ray data was taken with the Chandra X-ray Observatory. This spectrum was observed with the Suzaku X-ray Observatory, but they're actually very similar detectors. So the Chandra spectrum looks quite similar. And what you can see, again, just with your naked eye from this, is that you have these very bright, strong emission lines from highly ionized oxygen and highly ionized neon. And so this tells you right away that it's the amount of chemical enrichment here, and also the state of the plasma to produce these ionized species. Okay, so one thing I'd like to stress is that most of the X-ray imaging detectors that have flown over the past 25 years are integral field units, especially X-ray CCDs that have flown on missions like Chandra and Suzaku and XMM. So the way that these work is a little bit different from optical CCDs. Instead of one photon producing one electron's worth of signal, so that you're essentially measuring the flux of the source. A CCD, because X-rays are not as copious as optical photons, the CCD counts individual X-ray photons, and the signal recorded is proportional to the photon energy. And so you're able, in an image like this, to produce a spectrum in any particular part of this image. And that's why this is essentially an integral field unit. Now, for silicon-based CCDs, the spectral resolution is not great. The resolving power, which is the energy divided by the spectral resolution, is on the order of 10 to 40. And so anybody who does optical spectroscopy knows that that's not that's not very good. On the other hand, you get this for free, essentially, just the way these detectors work. Okay, so the idea here is that in order to understand the physics more, we really need higher spectral resolution to see what's happening in these lines and detect fainter features as well. So another thing you can do in the X-ray regime is to use dispersive grating spectrographs. Similar to optical spectrographs, these have a considerably higher resolving power, on the order of 1,000 for the state-of-the-art grating spectrographs that have flown on Chandra, the HETG, and on XMM, the RGS. And down here, you can see an example of this. So instead of measuring the energy through the CCD signal, you're just measuring the energy as a function of distance along the detector. But one thing you probably noticed from here, this is the same supernova remnant I showed before. If you disperse this, you get a little image of the supernova remnant anywhere. So extended sources degrade this resolving powers quite significantly, and you lose imaging information as well. In addition, these dispersive gratings have poor efficiency at high energies, just because it's difficult to diffract high energy X-rays. This is especially true at the interesting energies around 6 keV, which is the iron K band, where there's a lot of interesting astrophysics to explore. In addition, because you have this really long extended spectral trace, you need large detectors, especially if you want high dispersion and high resolving power, and that gets expensive to build and fly. So the next step in instrumentation for high resolution X-ray astrophysics, I would say, really is a true X-ray integral field unit. And that's what I'm showing here. This is the soft X-ray spectrometer that flew on the Hitomi mission about 5 years ago. And I'm going to talk a little bit about this works because, in fact, this is the same instrument that will fly on Chrism and do a lot of the really exciting science that I'm going to talk about near the end of the talk. So over here this is a picture of the actual SXS detector that flew on Hitomi. So this just gives you an idea of the size. So when holding it, this big picture I'm showing here is actually just this little square rectangle that's included here. And the size of the sensitive area of the detector is only 5 millimeters across. So each of these little squares is a pixel, and each of these squares is an individual detector. And so essentially you're making an integral field unit just by assembling a 6x6 array of these pixels. And I'll talk a little bit about how those detectors work, which gives them the exquisite energy resolution compared to something like a CCD detector. And so each of these pixels, if you zoom in, this shows a little 3x3 region of pixels. It's composed of a mercury telluride absorber, which is on top of a little silicon thermistor. And both of those, so those are linked together, and both of those are linked by some fairly weak link down to a heat sink, which in the case of the SXS was held at 50 millikelvin. And what happens is that when an X-ray comes in, like this little orange ball, it imparts a small amount of thermal energy. It actually produces phonons, but it imparts a small amount of thermal energy to that mercury telluride absorber. And this silicon thermistor is essentially acts as a thermometer. The resistance changes as it heats up, and that resistance is measured and recorded. And the signal you get out of this, as you detect photons, is a pulse in the temperature, a very sharp pulse, and then a pretty sharp exponential decay. And the height of this pulse is directly proportional to the amount of energy of the incoming photon. And so by counting these pulses and by measuring their heights, you get a very accurate measure of the energy of each incoming photon, as long as you only have one photon hitting a pixel at a time. Okay, so here's a little movie that I'm going to show, and I hope this works over Zoom, but this will show a better version of what I just showed. So this is the detector that I just showed. You can see here are the 36 pixels, and all of this other structure is required to keep it cool. So this is part of the cryogenic system that keeps this detector at 50 millikelvin. Okay, so I'll start the movie and it'll start zooming in to the detector. Okay, now it's just an animation, but you'll see X-rays coming in, and they impart a small amount of thermal energy to each pixel, and you can see they're color coded simply by the energy that they impart. All right, and so each pixel is now independent from every other. So as long as your optics are sufficiently good enough, you don't have to worry about the size or of the object degrading your spectral resolution, because you can resolve that spatially. And so that's what was done for Hitomi. So this is a spectrum of the Perseus cluster that was observed with Hitomi just about 6 years ago, shortly after it launched, and observed with that microcalorimeter. And so what I'm showing here, this is the field of view of the microcalorimeter. It's actually 3 arc minutes on a side, and I'll have a little bit more on the Hitomi results later in the talk. And it's superimposed on a Chandra image of the Perseus cluster, because Chandra has the best spatial resolution of any flying X-ray mission. Hitomi's spatial resolution was considerably worse, and Chrism's will also be considerably worse. And I should also point out that this is the Perseus cluster is a galaxy cluster, so it's filled with very hot, many millions of degrees Kelvin gas that makes up about 90% of the baryons in the cluster. So this material dominates the baryon budget of galaxy clusters. And in the center here, you can see a lot of structure, and this image has been processed so that the bulk of the emission has been removed, and this is essentially a residual map, which shows all of these kind of bubbles and indications of activity in the past from this the supermassive black hole at the very center of the central galaxy of the Perseus cluster. And so we aimed the Hitomi SXS at this, and this is the spectrum that we got from this entire field of view. And a spectrum, this is really a new window into X-ray spectroscopy. A spectrum like this had never been observed before for the Perseus cluster or for any other cluster. And so, one of the real things you see here is this helium-like iron line, this iron 25 line, so iron that's been ionized until only 2 electrons are remaining, which is a very strong line that we've seen before, but not at this resolution, because you can clearly see there are multiple components, which is not unexpected. I'll explain that in a bit. And you can see all of these other faint lines, which have never been observed in this cluster before, which, even just looking at them reveals a lot of information. But then if you actually study them in detail, it reveals a huge amount of information. This observation was on the order of 250 kiloseconds, which is long, but it's sort of a moderate observation, especially for a target like this. Okay, so this was really exciting. When we first saw this spectrum, we were really excited to do a lot more science with Hitomi. Unfortunately, shortly after these data were taken, the Hitomi spacecraft was lost due to an operations mishap. And so it lasted for 38 days, and unfortunately there was an attitude control error that caused the spacecraft to spin out of control and break apart and no longer be useful. Prior to that, however, I do want to point out that thanks to the hard work of the instrument teams, everything had been working perfectly, which was fantastic. So we did manage to observe 6 targets with Hitomi before it failed, and have more than 13 science papers. I think we have even considerably more than that at this point. These were the targets that we observed. I'll point out that the Perseus cluster was the only target that was only line-rich target for which we got a very good amount of data. Most of these other targets do not have emission lines. In fact, they're calibration sources, which is why we observe them. N132D is a supernova remnant, but the exposure on that was very, very short. So we didn't really get much data. But what we did get, especially from the Perseus cluster, was a very brief glimpse into the power of high-resolution X-ray spectroscopy and just how much it can transform X-ray astronomy for future missions. And that was very exciting. And so shortly after Hitomi's demise, there was a plan launched to recover the science by flying a replacement mission for Hitomi. And that's what XRISM is. So now we'll talk a bit about XRISM and its instruments and its science goals. XRISM is an acronym. It stands for the X-ray Imaging and Spectroscopy Mission. And its main goal is to perform high spectral resolution imaging spectroscopy across a very broad X-ray band. And these are the 4 science pillars that have been identified, which are actually closely related to the Hitomi science pillars, since no mission has been launched since then that can address these in the same way. The first one is to explore the formation and evolution of structure in the universe. And in particular, the questions we'd like to address are how cluster mergers turn gravitational energy into thermal energy. And in that process, how much energy is distributed into motion in that hot millions of degree intercluster medium, which dominates the baryons in the cluster. And I will talk more about this at the end of the talk, because this is the science that I'm quite interested in. In addition, XRISM will explore the circulation of baryonic matter in the universe, especially how feedback from supernovae and AGN distribute heavy elements and other baryons. And also how energy is transported and circulated in the universe, especially how galaxies and their supermassive black holes evolve together, and how those supermassive black hole AGN, along with X-ray binaries, how the accretion flows and the winds work in those objects. And whenever you have a new capability that you put into service, new astrophysics always appears. This was certainly true with Chandra, which was the first high spatial resolution mission to fly. And this was true even with that modest Perseus cluster observation with Hitomi. So we expect that XRISM will usher in new astrophysics, or enable us to do new astrophysics, such as exploring the plasma conditions in supernova remnants, which are these transient objects where we expect to have very non-equilibrium plasma conditions. Also validate laboratory measurements, which we're not actually able to do in the conditions that they are in space on the ground. And also search for things like dark matter, or have new, completely new detections of things. So XRISM will greatly expand a new era of spatially resolved X-ray spectroscopy that was started by Hitomi 5 years ago. Okay. All right, so I'll talk a little bit about the mission and the instruments. As I mentioned before, XRISM is led by Japan, by the Japanese Aerospace Exploration Agency, with important contributions from NASA and ESA. It is nominally a 3-year mission. As I'll show, the microcalorimeter instrument needs to work at 50 millikelvin, and so it requires liquid helium cryogen to do that. But in fact, there is a mode, once the liquid helium cryogen runs out, that we can run it without cryogen. And so, in fact, it does not have an upper limit to its lifetime. It hopefully can run for years and years once it's on orbit. It will be in a typical orbit for Japanese missions, which is a low Earth orbit, an inclination of about 30 degrees. And right now, the launch is planned for Japanese fiscal year 2020. And so that means no later than March of 2023. There will be about 9 months of initial phase time, which is 3 months of commissioning to make sure things are working out properly, make sure we don't make the same operations mistake with the attitude control, especially. And then 6 months of what's called performance verification phase, which you can also think of as science working group time, where targets selected by the science team will be observed. This phase really is to demonstrate to the community the capabilities of XRISM. It is not to do all of the very interesting science and leave nothing left for the community. And so after the first 9 months, there will be multiple guest observer phases that anybody in the world can apply for time on. And there will be lots of science left over after the science team does these initial observations. We're making sure that that happens. I will point out that the guest observer phase, there will be calls in the US for US observers, Europe for European observers, and Japan, I believe, will handle proposals from Japan and also the rest of the world. So if you're not based in US or Europe, you can propose for guest observer data through Japan. XRISM will fly 2 instruments. This is 2 instruments that flew on Hitomi have actually been removed, 2 hard X-ray instruments, just to save, just to make it easier to build this in a timely fashion and also make it cheaper. The instrument Resolve is the replacement for SXS. So this is the microcalorimeter. It has a 3 arc minute field of view, it has a goal for a spectral resolution of 5 eV across the entire band, which if you do X-ray astronomy, you see this is quite broad, from 0.3 to 12 keV, so more than a decade of energy coverage with high spectral resolution. I will point out that the point spread function, the spatial resolution, is not very good. It's on the order of 1.5 arc minutes, which is the same as what Hitomi was, very similar to Suzaku. But the point of this is to have modest imaging with very high spectral resolution. And then it will also fly Xtend, which is a wide field instrument covering almost 40 arc minutes on the sky. It's CCD based. The real exciting thing here actually is that there's this high energy coverage, which is considerably higher energy than Chandra or XMM or Suzaku was. Okay. There's a lot of information on here, which I won't go into detail about. This is the requirements for what Resolve has to do. Okay, and so these are actually the same as Hitomi. These are the requirements. But what we can do now is, because Hitomi flew and was operational for 38 days, we can write down what Hitomi actually did. And I'll point out that Hitomi exceeded all of the requirements, some of them by a lot. It met the goal for the spectral resolution. The background was very low. And finally, the cryogen mode lifetime with the liquid helium, instead of the requirement of 3 years, was projected to be more than 4 years, which is great because that greatly improves the operational efficiency by using the cryogenic mode. Okay, so if we manage to get 5 eV spectral resolution again on XRISM, then at 6 keV, this will be equivalent to a resolving power of better than 1,000, which approaches what optical spectrometers can do. Okay. All right, so I'll talk a little bit about Resolve. Resolve is a high resolution imaging spectrometer. It's essentially a copy of the SXS on Hitomi, and it includes the X-ray mirror assembly, so it's all one instrument. I mentioned that the detector has to be cooled to 50 millikelvin. This is done, and I showed in that movie that very large part of the doer that's needed in order to cool it. And this is done in this sort of complicated multi-stage cooling system. And so you start with a liquid helium bath, which is at 4 K. There's a mechanical Joule-Thomson cooler, which cools that down to about 1 Kelvin. And then there's a multi-stage adiabatic demagnetization refrigerator, which is something that has to be cycled. So it's essentially just a big magnet that magnetizes a salt pill, and the magnetic field is removed. And as the magnetic moments of the salt in the pill randomize, that removes energy, that cools the system down. And so with this multi-stage ADR, we're able to get down to 0.05 Kelvin from an initial hot side value, if this is actually hot, of 4 Kelvin. Now, when the liquid helium runs out, then this stage can be cooled to 4 Kelvin with an additional ADR. That reduces the efficiency a little bit because the ADR does need to be cycled. You need to go through this high magnetic field and then removal of that magnetic field. But even so, the efficiency will only be reduced to something like 90%, which is still really good for not needing cryogen. Okay, and so this entire cooling system is in a giant, a very large structure, which I'll show in the next slide. So the status right now is that the flight detector was delivered to Japan from Goddard Space Flight Center, where it was constructed. That happened back in late 2019, and over the last year and a half, it's been undergoing testing and calibration, and it's been integrated with the flight doer in Japan. The mirrors are currently, they've been constructed, they're currently being tested and calibrated at Goddard Space Flight Facility in the US, where they were constructed. All right, so this gives you an idea of the cooling system. So here is that little detector being held by someone. So here it is inside of the calorimeter spectrometer insert, and you can see all of these isolation devices that prevent vibrations from producing signal in the pixels. In addition, you of course have to cool it. So this entire insert gets put in this little area. In fact, it's down here somewhere, surrounded by mechanical coolers and these multiple shells of multiple vacuum shells for this multi-stage cooling system. And so this entire doer is shown here in Japan. You can see a person in the background here. So this doer is on the order of 2 meters tall. You go from a detector, which is about 5 millimeters across, to a doer, which is on the order of 2 meters in height. So the detector, the thing that's actually doing the detecting, is this tiny little device buried somewhere in the heart of this very large, very heavy system, meant to keep it cool. Okay, so just a little bit about its performance. This is data that was taken at Goddard Space Flight Center before the detector was shipped to Japan. The x-axis here is the spectral full width half max at 6 keV in EV. And it's just plotting the number of pixels, number of the 36 pixels and their spectral full width half max. And so you can see that all the pixels have less than 7 EV full width half max, which is the requirement. And almost all of them, except for this one, are less than 5 EV. In fact, many of them are near 4. So this is fantastic. This is what the Hitomi device showed also when it was at this stage. Once it gets integrated in the spacecraft, this is likely to degrade just because of noise sources and things like that in the spacecraft. But this is certainly the first step in having a well-functioning instrument. All right, so in addition to Resolve, Chrism will fly a second instrument called Xtend, and the names are meant to reflect what they do. So Resolve, in addition to showcasing the resolution of the team to successfully fly this instrument, will of course provide high spectral resolution imaging. Xtend extends the field of view of Resolve, and it really is a support instrument for Resolve. This is a wide field X-ray CCD imager based on, essentially copied from the soft X-ray imager on Hitomi. It's, the way the CCDs work is very similar to the CCDs on Chandra or Suzaku or even XMM. They are a little bit different. There are 4 of them in this 2x2 array you can see in this picture over here. They're actually quite thick. They're 200 microns thick compared to about 50 micron thickness for the Chandra CCDs. And they're backside illuminated. So what this means, the backside illuminated means they have very good quantum efficiency at low energies because there isn't a lot of structure on top of the CCD to absorb soft X-rays. The fact that they're thick means that they also have very good quantum efficiency at hard X-ray energies because there's a bulk of silicon to stop X-rays up to energies of about 12 or 13 keV. In addition, it will have a low particle background because it's in low Earth orbit. So this is similar to Suzaku. And it's got a very wide field of view of about 40 Earth minutes on site. So if you look at this image, this is an image of the COMA cluster. I believe this image comes from ROSAT, but you can see all of this X-ray emission from the very hot gas that fills the cluster. And then there are some shapes here that show the fields of view of different instruments. So those of you who've worked with Chandra or Suzaku, this magenta square shows the field of view of that. Here's the field of view of XMM. The field of view of Xtend is significantly larger than all of those, 40 arc minutes on a side. And this tiny little square here shows the field of view of Resolve, this 3 arc minute by 3 arc minute field of view of the microcalorimeter. So it really is a tiny footprint, and having Xtend here is valuable to, for example, identify any very bright point sources that might be nearby that might be contributing photons to the Resolve field of view because of the tail of the broad PSF. In addition, when we're staring at some object, for instance, like we're looking at COMA, if we're looking at the outskirts of COMA here with Resolve, we have a ton of data on the rest of the COMA cluster from Xtend, which will be very valuable. So Xtend, the flight detector has been constructed. It's undergoing testing and calibration right now. Again, the mirror will be a twin of the mirror that's being built or that has been built for Resolve, and that mirror has been constructed and is also undergoing testing and calibration at Goddard. This just shows a picture of the Xtend in its housing. So it's got this bonnet to reduce stray light, and then it has these 4 mechanical coolers to cool the CCDs down to about -100 Celsius, which is its operating temperature. All right, and then finally, in terms of the mission, just to compare its capabilities to other instruments, these are a couple of figures of merit that I think are good to show what it can do. So there's one on the left here. This is for Resolve. The one on the right is for Xtend. So if we look at the one on the left, This is showing a figure of merit for the ability of Resolve to detect weak emission lines. And show as a function of energy, it's showing the effective area divided by the spectral resolution. And so the lower the spectral resolution, the higher the effective area, the bigger the more capable you are detecting weak lines. And that sort of makes sense because the narrower your line spread function, the less continuum that is mixed into the line that you have to deal with. And obviously, the higher your effective area, the more photons you get. So both of those go into detection of weak lines. The blue and purple show Resolve, how good Resolve does. The purple is for the goal of 5 eV spectral resolution. And then this brown and this green show the best state-of-the-art figures of merit for existing instruments, XMM RGS and Chandra HETG. And once you get above 1 keV, Chrism is an order of magnitude better than both of these instruments. And when you get up to this 6 to 10 keV range, it's even higher than that. So this will really open up a new realm that we haven't been able to explore before. I've also put Athena on here. Now, Athena will not launch before the early 2030s. It's right now in the design phase. But that will fly an instrument called the XIFU, which is a very similar microcalorimeter device, but of course, more advanced, more than probably 20 years of technology advanced. And that will be another order of magnitude increase in this metric, which is just fantastic. But between when Chrism launches within a year or two and Athena launches within 15 years, Chrism will be the dominant instrument for this particular science. Okay, and then moving over to Xtend, this is showing as a function of on-axis effective area, the grasp, which is simply the effective area times the field of view in square degrees. And so Xtend, due to it having very good effective area and having a very large field of view, really has tremendous grasp, more so than any other non-survey mission that has flown. Now, I will point out, I did not put eROSITA on here because eROSITA right now is a survey mission. But this, is combined with the deep pointings that we'll do with Resolve. I think Xtend will return some very interesting science in its own right. Okay, so in the last part of my talk, I just want to talk about some science that we plan to do on galaxy clusters with Chrism, as well as a little bit of a review of what was done with Hitomi. All right, so this is showing actual data from Hitomi of the Perseus cluster, which is the same spectrum I showed earlier. This is an image from the SXI, which is the equivalent to Xtend that will fly on Chrism. And so you can see all of this emission from the very hot gas distributed in the Perseus cluster. Now, this little square shows you the field of view of Resolve. If you zoom in on that, I'm now showing the 36 pixels. In fact, there are only 35 pixels for a reason that you can ask me at the end. But these are the 35 individual pixels of SXS in this case. And again, this is just the SXI image now at a different stretch than it was in here. But you can see the SXS pixels are actually pretty big. They're 30 arc seconds on the side. Now the PSF is an arc minute and a half. So we're still sampling the PSF. Now, I've been stressing that this is an imaging spectrometer. The imaging, I will say, is not fantastic. However, you can clearly separate emission from this region of the cluster versus emission from this region of the cluster. And that's not something a dispersive grating could possibly do. You imagine taking all of this X-ray emission and dispersing it, you're going to end up with just a big smear of emission without being able to measure accurately any emission lines. All right, and up here, this is not the Perseus cluster. This is actually a simulated spectrum of the Virgo cluster, the core of which is the galaxy M87. And the point here is to show you basically that even though the spatial resolution isn't fantastic, in small regions, you can still get a very, very precise, very high spectral resolution spectrum covering a really broad energy band. And this dynamic range between the broadness of the energy band and the really fine spectral resolution across that band is something that just hasn't been done before. And you can see all these emission lines. And again, just looking at this by eye, this returns information that you just have not seen before. Okay, so this is the observation again of the Perseus cluster. So here again is the SXS field of view. And this is the Chandra map. And now you can really see this filamentary and bubble structure, which reflects activity from the central AGN of that central galaxy during the lifetime of Perseus. So it's clear there's been a lot of activity blowing these bubbles over the last several million years. And so what we were interested in this observation is we see spatially evidence of gas moving around, but we don't have any information on what its velocity is. We really don't know, just because we haven't had the spectral resolution to be able to measure it. And so the idea here is to be able to measure the line of sight velocity of this gas. And that velocity you can think of as in two different ways. There's a turbulent velocity, which is just sort of small scale mixing of the gas. And that should change the width of the line simply from Doppler broadening. And then there's also bulk motion. You can imagine large parcels of gas that are moving with respect to each other, or even all of the gas might be moving with respect to the local standard of rest of the cluster, and that will produce a shift in the line. Okay, and so this is a spectrum showing what we observed. This is now zoomed in from the version I showed before into this iron 25 line, which now you can see is actually composed of 4 lines, which I'll show in a little more detail in the next slide. And you see all of these lines that you never would have seen before, especially the manganese line and this chromium line, which are important for understanding chemical composition and the importance of different kinds of supernovae in enriching this gas. I will point out this red dashed line. This is the previous best version of a CCD resolution spectrum. And so, yes, you can certainly detect this iron 25 line, but you can't measure its width. You can't differentiate these different components in it. So the amount of information you get from CCDs pales in comparison to what you get from a microcalorimeter. Okay. All right. So zooming in now on that iron 25 line, this is a spectrum that was taken from the first Nature paper that we wrote from the Hitomi result. Again, you can see the red line and the data points. These are the Hitomi SXS data. This blue, again, shows the Suzaku CCD spectrum, just for comparison. And this line is now decomposed into 4 components. This is a triplet emission line. So there's a resonance line here. That's what the W means. This is a forbidden line, and there are 2 intercombination lines that all contribute. And so by measuring the relative strengths of these lines, you can certainly tell if this is an equilibrium or not. In fact, it is. There's some evidence of resonance scattering, which isn't shown here. But another thing that you can tell is simply comparing the line width to the instrumental line spread function. You can tell that the line width is considerably broader than the instrumental line spread function. And this is a really exciting result. I know in optical spectroscopy, this is kind of ho-hum, but in X-ray spectroscopy, this is pretty exciting, especially at these energies. Okay, so the purple shows the instrumental line width, and you can clearly see the red is considerably broader than that. So if you measure the extra broadening and assume that it's due to Doppler broadening, probably due to turbulent motion, then you can constrain the turbulent line width to be about 164 kilometers per second. Now, that's very low compared to the sound speed in this cluster, which is thousands of kilometers per second. And compared, even just when you look at this image, you see all of this structure that was produced by feedback from the central AGN. You kind of expect that things would be disturbed in the center, and the turbulent velocity would be considerably higher, and the bulk velocity would be considerably higher. But in fact, it's not. This is a very low turbulent velocity to measure in a system where we see these sorts of features. So this was somewhat surprising. It was actually very interesting. Another thing I'll point out here is that this line contains 21,000 counts. Only 16 of those are due to background. And this is for a 250 kilosecond observation. So the background on this is very low, which again enhances its ability to measure faint lines. This is not a faint emission line. This is a very bright emission line. Okay. All right. So we've seen that the turbulent velocity is low. The bulk velocity also is fairly low. This is now showing a few pixels binned, but it's color coded by the velocity of the gas, the velocity measured from that iron 25 line in those regions. And so the red material is moving away from us, the blue material is moving towards us. And the difference is, this was for a press release, so the numbers are in kilometers per hour and miles per hour. But these differences are also on the order of about 150 kilometers per second. So we see turbulent velocity that's low, 150 kilometers per second. And we see some evidence of bulk velocity, but that's also fairly low, especially compared to the sound speed in this gas. So we concluded, the ICM of Perseus, at least in the center, seems pretty quiescent, especially given just what we see visually in all of these bubbles and activity. Okay, so that's Perseus. Now, another thing we're interested in exploring is what are the motions of the gas further out in the cluster? The center of the cluster is dominated by feedback from the AGN. When you get further out in the cluster, you expect different kinds of contributions. And so this is work that we hope to, we didn't get a chance to do with Hitomi, we hope to do this with Chrism, and this is something that I'm particularly interested in. So galaxy clusters, because they're the largest and youngest structures to be virialized in the universe, they encode information about cosmology. And in that way, they're vital tools for probing cosmological parameters. I know that people on this call who are intimately familiar with this. So in general, this requires measuring cluster masses, and then you either can simply get a mass distribution, and the number of clusters of different masses traces it back to the cosmological parameters that rule the universe when these things were forming. Or you can be a little more careful and get the baryon fraction and measure that versus redshift. That also gives you information about how clusters formed over the age of the universe. Now, it turns out X-rays are very efficient to do this, simply because, as I mentioned, these clusters emit copious amounts of X-rays. They're easy to detect. And the X-rays are produced by gas that is 90% of the baryons in the system. So you're really tracing the bulk of the baryons. However, if you do this, you're assuming that all of that hot gas, the emission from that hot gas, is dominated by gravitational heating. So it's in hydrostatic equilibrium. And so all pressure support is due to gravity. That assumption can't be true, because we know there has to be some non-thermal support against gravity. We know there has to be motion even in the outskirts of galaxy clusters, where mergers and ongoing infall of substructures have to be producing some kind of bulk motions and turbulence. We just don't know how important it is. We don't know what fraction of the pressure support is due to this turbulent and bulk motions versus just thermal gravitational heating. And so that's one thing we want to explore with Chrism. How important is non-thermal pressure support? And so how biased are cluster cosmological constraints from this? Okay. So this is a little technical, but the idea here is that simulations, hydrodynamical simulations of structure formation, and careful measurements of the gas fraction of clusters suggest that the thermal pressure support, the non-thermal pressure support is on the order of 50 to 20% of the total pressure support. That's what I'm showing over here. So this is a plot showing the radius as you go out in the cluster as a function of R500. R500 is just a scale radius that is very useful. It's the radius within which the average mass density is 500 times the critical density. So this is, typically a radius that's used kind of as a pinpoint or a scale radius in clusters. And this is showing the fraction of total pressure that's in non-thermal pressure. And you can see this band basically covers from 5 to 20%. That's a really broad band. 20% actually is pretty important, because this would bias the masses significantly. 5%, on the other hand, means that there really isn't much bias. So constraining this is quite valuable. I will point out that there are some results that indicate it's fairly low, but these rely on some assumptions about the gas fraction. And what we really want to do is measure it directly. We want to be able to measure the velocity of the material out as far as we can in the cluster to measure directly what the contribution of motion is to the pressure support. And so we can do that for a hot cluster. For instance, a cluster at 8 keV, that's the temperature of the hot gas. This is about 80 million Kelvin. And for this kind of cluster, the expectation is that even for 5% non-thermal pressure support, we expect the turbulent velocity, the Doppler broadening of the lines, to be about 250 kilometers per second, the bulk velocity to be 100 to 200 kilometers per second. And that is easily detectable given the spectral resolution of XRISM. And that's just the 5%. If it's more than that, these numbers will be larger and much more detectable. Okay, so Hitomi has only been observed, Perseus was only observed in the core by Hitomi, where effects of the AGN are strongest. So we want to look at something outside of the core. And so the idea here is that we need a cluster which is relaxed because we don't, we don't want obvious merger signatures to alter the data, alter the result we get. And we need to go far enough out in the cluster that we're sampling away from where the AGN activity is. But it can't be so far out that the surface brightness is way too low that we can't make a measurement. And so after a lot of work, we've sort of settled on a location where this is an interesting measurement, and that's at just at R2500. R2500 is nearer in than R500. It's about 500 kiloparsecs out, but well away from the core where effects of the AGN are important. All right, so Abell 2029 turns out to be a really good target to do this in. It's one of the most relaxed clusters in the universe. It's at a distance where the flux is still high enough, but you can put this pointing from resolve out far enough from the core that there's not so much scattered light from the core making it into that region. And this is actually an issue because of the fairly poor spatial resolution of XRISM. There are some other targets to do this in, which I point out here. Those who are study clusters, I'm sure, recognize all of these objects. Some of these are in the PV phase for other reasons. Some of them are calibration targets. I will say that I expect all of these clusters will be observed at some point in the XRISM mission, perhaps by some of the people who are listening today. Okay, so the idea now is to measure the line width and the line shift from those bright iron, highly ionized iron lines in this region. And so this shows a simulated spectrum of that. This is simulated now for 250 kiloseconds. I should point out this image, this is a real image of Abell 2029 taken with XMM, which we use to do these simulations. Now, this will have contributions not just from this region, but in fact, there will be contributions from other regions as well. And so we need to worry about disentangling that information because, for instance, if we have photons from the center that are being scattered into this region because of the broad tails of the PSF, if the velocity structure is very different in the center than this region, then that velocity structure can bias what we measured here. But we think we can do this. And so with the simulations we've done, basically have taken photons from each of these three regions, seen how many end up in this region, and that's what these different components are for the spectrum. So you can see that even from this just interior annulus here, it's about an order of magnitude fewer photons produced or collected in that region from this annulus. And from the core, it's another order of magnitude down, or maybe a factor of 5. Nevertheless, you can imagine that if this line shape is very different in the center, then that could affect the overall line shape that we see in the black here. And so, in fact, what we need to do is we need to measure the velocity in each of these three regions and do some simultaneous spectral fit where we constrain the velocity structure in each of these regions. The ultimate goal is to measure what it is here, but in fact, we'll get some really interesting information about the velocity structure at the core, as well as at intermediate regions as well. And then in the future, this is a fairly expensive observation. This is 300 kiloseconds to do this. But in the future, you can imagine doing another arm so you can search for azimuthal variations in that velocity. Okay. I know I'm running out of time, so I do want to point out that, again, while you're observing this small square 3 arc-minute region with resolve, Xtend will image the entire region on this side of the cluster. Now, this is about 2/3 of the cluster, and it will observe it for 300 kiloseconds. So this is a pretty exciting extension of the Suzaku cluster outskirts project that I think will be able to compare the results from XRISM to the results from Suzaku. Okay, so I don't have time to talk about Virgo, so I think I will skip that. And if anybody wants to ask me questions about it, I would be happy to answer questions about it. Okay, the last thing I do want to talk about is going from Chrism to Athena. I showed this before. Athena will have an order of magnitude better performance in terms of detecting faint emission lines. That's not the whole story. Athena, which will launch hopefully within the next 15 years, will have significantly better spatial resolution and significantly better effective area than Chrism. So Chrism is a pathfinder for Athena. Chrism will certainly do a lot of exciting science. Athena will again be transformational in this science by improving the spectral resolution by a factor of 2, improving the spatial resolution by a factor of 10 or more, and also having many more pixels. Again, if you think of each of these pixels as a little detector, imagine having to make 4,000 of them versus just 35 of them. But you can see again, here's the Perseus cluster. Here's pretty much the best we could do with Hitomi in terms of measuring bulk motions of gas. This is the equivalent for Athena. This is a simulation, but you can see you're starting to see this velocity structure on much smaller scales, on the scale of these bubbles and cold fronts and slushing things and things like that. So this really is the wave of the future. And then Lynx, if it is approved and ever happens, will be another step even beyond what Athena can do. Okay, so just to summarize, Chrism will launch within the next 2 years. It will continue a new era of exquisite X-ray spectroscopy that was begun with Hitomi. We have released the PV target. Just go to Google and search for Chrism PV target list and see if your favorite target is on there. I will point out that the guest observer phase, there will be lots of science to do in the guest observer phase for the next 5 or more years. And I want to thank the Chrism instrument teams. I don't think any of them are listening, but they've really done a lot of heroic work over the last year through the pandemic to test and calibrate and integrate the instruments. Okay, and I just want to leave up this list of papers in case you're interested in exploring more about the instrumentation. So thank you. I'm happy to take some questions.
Okay, thank you, Eric, very much. It's a very interesting talk. So let's open for questions. I'm not sure. Someone you help me here. First, let's see the attendance. Please raise your hand.
Yeah, I have a question, in fact. So
Okay.
I'm not a X-ray person, so I can ask any question without fearing to be stupid, but
Please do.
So this satellite, will there be a call for proposals open to the community, right?
Yes, there.
Okay, and
there will be. So each space agency is doing it themselves. So NASA will issue a call for U.S.-based proposal, and my understanding is that JAXA, the Japanese space agency, will issue a call for everybody who's not based in the US or in Europe. That's my understanding.
And is there any project like a large area survey for new X-ray sources? So I believe that in this way we could find, for example, some new black holes in the galaxy. I don't know, and
yeah.
But I think in this case you would need only not a very good resolution, but large spatial coverage, isn't it?
Exactly, that's right. So because of its limited field of view, and I'll just go back to this one's probably good. Because of the limited field of view of Resolve, which is only 3 arc minutes on the side, it's not good for that sort of survey science. And Resolve really is the primary instrument on here. Xtend, while it is good for survey science, it has a 40 arc minute field of view. It really is not, that instrument does not drive the science. And so the science throughout the mission for Chrism will be driven by what Resolve can do. And yeah, so surveys are not what it's good at. So that will have to wait for something like Athena, and Athena will certainly be doing surveys for exactly that, for distant AGN, both in imaging and in spectroscopy.
Mm-hmm. And for example, let's suppose you have a survey and detect new X-ray sources. And what kind of counterpart you would need to define what kind of sources that is, if it's a pulsar or I don't know, a black hole, or what kind of counterpart, maybe optical, in the optical, I don't know, what you need more to define what's the source.
Yeah, that's a very good point. So I will say that Xtend, because of its large field of view, the expectation is that it will find a lot of transient sources or a lot of new sources. So even though whatever target is being observed is being observed because of resolve, in this field, there probably will be sources popping up. And you know, I think what will happen is what has happened. So in fact, I should point out that there will be an effort to identify these new sources quickly, you know, sort of on a daily basis, or maybe 2-day basis, and then probably send that information through an astronomer's telegram for follow-up with other facilities. Now, the facilities that do the follow-up, that probably is up to the facility, and it's probably up to whatever the source is. But you can certainly, you know, you could follow these things up with Magellan, depending on what it is, or with radio telescopes if it's something like a pulsar that's been identified. And of course, the converse is true. So if a source is detected, say by LSST or something which is a really good survey instrument, or even by LIGO, then there is certainly the possibility that XRISM will be able to go to that target, or the place where that target was detected, and observe that field to try to detect something. So there is a plan for these so-called target of opportunity proposals, where the observation hinges on something new, a transient being detected with some other facility. And you know, I think the follow-up time is probably 48 hours, I think is the minimum amount of time. So it's, yeah, so it's not necessarily very good for following up like LIGO targets and things like that. But it's possible.
Okay, great. So we have a question here. Let me just promote Wendy to. Okay, Wendy, you can open your microphone to ask. Yeah, okay.
Hello. Thank you for the nice talk, Professor Eric. So I have a question. When you was talking about the science goals for the XRISM, you briefly mentioned about dark matter. So could you elaborate more onto that? How XRISM can shed some light on the dark matter issue? Please?
Yeah, I sure can. So actually, I think I have. If you'll bear with me, I think I actually have a slide on this. Here it is. Yeah, I can. So actually, this was already addressed a little bit by Hitomi. So you might know that there was a result that came out a few years ago now, which basically took very long exposures of the Perseus cluster, the same cluster I've been talking about, observed with XMM. And the idea was to search that spectrum, which was very high signal to noise, for emission lines that showed up in places where we don't expect emission lines. So places where there aren't atomic transitions that we know about. So this was work done by Ezra Bulbul and Maxim Markovich, Randall Smith, a couple other people. And so they detected a very faint feature at 3.5, actually 3.55 keV which seemed like it could not be due to any sort of atomic transition that we know about. And so the suggestion was, and this was, I will point out, this was just a suggestion for them, that this could be evidence of a decay line from a sterile neutrino, which is one of the possibilities for dark matter. And so you would expect if sterile neutrinos exist and they are dark matter, then they would probably produce emission. They would produce annihilation lines in the X-ray band, which would be observable for X-ray instruments. So the problem with XMM is that it has CCD spectral resolution, and so the line that was detected was broadened by the CCD spectral resolution, and so you're trying to detect a very faint line with a very poor resolution spectrometer. It's not easy to do. There's also lots of systematic effects because you have to worry about then the continuum on either side of the line and be able to subtract that perfectly. And if there's some instrumental feature there that you don't know about, that can really change your detection in a systematic way. So the SXS on Hitomi and also Resolve on Chrism are very high fidelity spectrometers. They don't have the same kind of systematic effects that CCDs do. And so in addition, just the resolving power is much higher, which really helps you detect faint lines. And so this is, if you remember that metric I showed for faint line detection, this is exactly what Chrism will be good at. So this shows that same Perseus observation from Hitomi that I showed before, but now it's a different energy band. I was looking at up at 6 keV at the iron 25 line. And so, we got data at 3.5 keV, and it showed that there is no line of the same strength that was observed in the XMM data. That's what's being shown here. I don't actually remember what these different colors are. I think these are lines that are put in here at the line flux that was measured in XMM, but for different line widths, because XMM was not able to measure the width of the line. And so even if the line is pretty broad, Hitomi rules out that line being there. If the more narrow the line is, the more heavily it rules it out. But you can imagine by the same token, if you do a very deep observation with Hitomi of the Perseus cluster or some other object which has a lot of dark matter in it and not very complicated baryon physics, then you can just search that spectrum for lines that look like this. Mm-hmm. And that's the idea, is to you'll get this information essentially for free from any cluster you observe. And so just a blind search for any emission lines in that spectrum, will tell you possibly whether there's a dark matter signature, or it could rule out certain sterile neutrino signatures to a very high precision. So that's the idea.
Okay, thank you.
Sure.
If I can make another question, can I?
Yes, go ahead.
Well, it's fine with me.
Thank you. Yeah, because I'm mostly interested in cosmology, so I'd like to see you comment more about how Chrism can help to get rid of the bias in cosmology. You mentioned about the turbulence, something like that.
Yeah, so let me go back to that. Okay. Excuse me. Okay, so I can talk a little bit more about this. And actually, let me go back to this. So the key here is that in order to do cosmology with clusters, it's really kind of it's a simple thing to think about. What you need to do is you need to measure the mass distribution of clusters as a function of redshift, and since clusters in a simple model, formed from little density fluctuations very early in the universe, the distribution of masses that clusters have today and at different places in redshift, you can then trace it back to the scale of those small mass fluctuations, small density fluctuations early in the universe. And those density fluctuations, those are driven by cosmological parameters. So that's the underlying idea here. And so all you need to do then is to measure the mass of every cluster in the universe, and you'll be able to trace that back to those density fluctuations and constrain cosmology. Of course, that's difficult to do, but it's not very difficult to estimate the mass of a particular cluster. And you can do this from the X-ray just by measuring the luminosity and the temperature of the bright intercluster medium. But you do have to make the assumption that all of that hot gas started out, as this large cloud, and the reason it's hot is because it has fallen in to the gravitational well of the forming cluster and been heated by that loss of gravitational potential energy, right? So there's a clear relation between the collapse of an object and the amount of gravitational potential energy that's put into heat versus being radiated away. And so that's pretty straightforward to do. But it assumes then that once the cluster is formed and you measure its luminosity and temperature, you're assuming that the only thing that that happened as it was forming is that the potential energy was turned into thermal energy. But in fact, some of that potential energy could have been turned into kinetic energy and motion of gas. And so if you don't know how much of the energy was converted into kinetic energy, then you don't know, you don't have a correction factor to make for the erroneous assumption of hydrostatic equilibrium. And so the idea basically then is to use XRISM to directly measure the velocity of the gas at different places in the cluster. And that will give you an idea of just of the correction factor you need to make for this assumption of hydrostatic equilibrium. Okay, and so you can do this with simulations, but of course, as we know, simulations aren't perfect because we don't know the exact initial conditions, and they don't necessarily include all of the astrophysics that we certainly know is happening. Things like radiation and mechanical feedback and things like that are difficult to include in simulations. And so the simulations do have a prediction about how much pressure should be in this so-called non-thermal pressure support. And it should be on the order of 5 to 20%, which is small. But as I mentioned, I think this 20%, if it really is that high, that 20% of the 20% of the pressure in the cluster is a result of motion as opposed to thermal energy, then that biases the mass. You're not measuring all of the pressure when you measure the temperature and luminosity of the gas. And so that biases then the mass low by, I think for 20%, it's on the order of 30%. You're misestimating the mass. And so suddenly your clusters are less massive. You think they're less massive than they actually are. And so when you trace that back to the initial primordial density fluctuations, you get the wrong cosmology. Okay. And so, XRISM will be able to measure directly the velocity structure in various places in a cluster and in various clusters. And so that will constrain this non-thermal pressure support, and then give you a correction factor you can use for the assumption of hydrostatic equilibrium.
Carlos Andres has a question too. You can open your microphone, Carlos.
Yes. Can you see me and listen to me?
Yes. Yeah.
Okay. Good. So, hello, Eric. This was a very nice talk. I'm also not an expert in X-ray, but I just wondering. Well, it seems to me that X-ray observations in X-ray require a lot of restrictions, but it also offers a good insights of different kind of physics that it's not achievable in other bands, of course. But I just wondering if with this the observation, some part of the observation plan will observe some of the same fields that were observed before, or are you looking for new fields? I don't know if it was clear.
Yeah, that was clear. So we will observe some of the same fields before. So I'll just go back to the list of slides here. A second. The list of targets that we've observed. So as I mentioned, Hitomi only worked for about 1 month. So it wasn't able to do very much at all. These are the targets that we looked at. So we will certainly observe the Perseus cluster again. Part of that is so that we can confirm that we have the Hitomi results, and so we can confirm with Chrism that they're the same, which is actually pretty important from an instrumental point of view. Also, I didn't mention this, but all of these data were taken with the gate valve closed. So if I go down to a picture of the, let's see, this is actually a pretty good picture. Okay, so you can't see it here, but this is the aperture. So this is the opening that X-rays go through. They go into this aperture. The detector is somewhere down here. But of course, this whole dewar has a big cover on it, and you can see that here. And in the middle of this cover is what's called a gate valve. It's basically just a big door that's closed, because when you launch the instrument, you want to make sure that the whole thing is sealed. You don't want material from exhaust from the rockets getting into the detector, because the detector's at minus 50 Kelvin. It'll just, 50 millikelvin. It'll just freeze on the detector and ruin your efficiency. So there's essentially a door that's closed here, but that door does have a window in it. It's got a window made of beryllium, and beryllium absorbs X-rays below 2 keV. So all of the data that we took with this, that door was closed because it has to stay closed for a month or so to let everything outgas and become stable. But what that means is that we didn't detect any X-ray photons below 2 keV. It was all above 2 keV. Once the door opens, which it will on Chrism, hopefully, and it should have on Hitomi, then we can detect a lot of low energy photons, and so that will expand the physics that we're able to do. And so, for instance, if I go to this spectrum, here we go. So again, this is a spectrum of the Virgo cluster. And you can see, if we had observed Virgo with Hitomi, we only would have gotten information up here. We wouldn't have gotten any of this data down here. And Virgo is pretty similar. There's a lot of data below 2 keV that where the photons are absorbed by that window that we just didn't observe. So we want to see what's happening at low energies in Perseus. Another target, N132D, which is a supernova remnant. As I said, we only got about 17 photons. We only detected 17 photons from that, just because the pointing wasn't good enough, so the target wasn't in the field of view for most of the observation. So that we certainly want to repeat that, because we want to get tens of thousands of photons, which we should be able to do. And there, a number of the other sources that were observed were calibration sources. So we'll certainly observe those again, because they're still calibration sources. But there's a lot that we didn't manage to do with the 6 targets that we observed with Hitomi that we'll do with Chrism.
Okay. No, yes. I see that you explained during the talk, but thank you for explaining again. And now it seems clear.
Sure. Yeah, my pleasure.
Okay, Simone, can I ask a first question?
Yes, Rebecca also has a question.
Okay, then Rebecca goes first.
Well, you can go ahead if a fast question.
Yeah, I'll make it fast.
Okay.
So, Eric, I'm going to pack everything in one single question.
Okay.
So, so rely on your memory.
All right.
So the Xtend and the Resolve, they go at the same time, right? It's like the XMM, the RGS. So you get all the photons at the same time. So
yeah, that's right. They each have a telescope.
Okay.
And they point at the same part of the sky. I can show you. Yeah. So this here, you see, this is the telescope for Resolve. This back here is the telescope for Xtend. So they're pointing at the same part of the sky. They're independent instruments, always observing.
Okay. So my concern was that I don't know. Naively, I would assume that probably the velocities, they're higher. Bulk motions, they're of higher velocity to be at higher radii from the center. So probably to get, I would expect that it would be easier to resolve things that are far away from the center. But you have the issue with the number of photons that you have, and the precision with which you measure that is the proportion with the inverse of the square root of the number of photons. So basically, you need a long exposure to do that. Exactly. But you get at the same time the two instruments. So every time you point at the center of a cluster, you get, I don't remember anymore the distance, you show the image there, you get a shot that goes up like 20 arc minutes away, more or less, I don't know, by eye. I see this off some outside part of the cluster. And I saw there that you have a resolution of about 250. You had two resolutions for the Xtend. I'm not sure the difference between the two of them. You have EOL and BOL or something like that. And but they were about less than 200 EV, right?
Oh yeah, for the spectral resolution, yeah. One is the beginning of life and one is the end of life because they suffer radiation damage, which increases the CTI. Just like Suzaku and Chandra. Okay, all right. So this still, even this resolution is not so bad compared to previous satellites. So if there is a higher, I don't know, if for example the predicted increase in pressure grows with radius, and the velocity grows with radius, two different things there. But maybe you could put constraints if you observe. If you're doing a point in the center for obvious reasons, like I did with Perseus, you could, for example, divide this exposure into many different parts and rotate around the cluster to get something like constraints on the velocities to, I don't know what they predict it could be. Actually, it should be the other way around. With 250 eV, what's the limit in the velocities for both motions you would be able to constrain a large radius with the Xtend? Yeah, so that's a very good point. And actually, I have not done that calculation. So I'll go back to this because I think this is what you were talking about. Yeah, you're right. If we have the cluster, even the cluster center in the resolve field of view, we'll get out to at least R200. And this is a typical cluster, but at least R200. And in fact, we'll have most of the azimuthal coverage. So we don't even need to rotate it that much. Mm-hmm. So what I'll say about that is that the spectral resolution will be pretty similar to XMM, maybe a bit. It actually will be similar to Suzaku. So it'll be similar to other CCD instruments because that's exactly what it is, and it's limited by silicon. There's a Fano limit to just how good the spectral resolution can be as a function of energy, but it'll be about 150 EV at 6K EV at the iron line. Xtend doesn't have nearly the effective area that XMM does. It's a factor of 5 or something lower, maybe 2. Actually, I'm not quite sure. So you'll certainly need to expose for a long time, or even just sum up a large azimuthal region, but that's not really a problem. The one thing that Xtend does have is a very low background, and actually I think that will help a lot compared to trying to do this measurement with XMM, which I know that you've tried to do. Another thing in your favor, as you say, is that the velocity does increase as you go out in radius, and that's shown in these results from simulations here. This is the non-thermal pressure support, so you can translate this into bulk velocity. I think into turbulent velocity. I think the turbulent velocity you're not going to be able to measure. You're not going to be able to measure the line width, just because there will be CTI effects that are stochastic, and so I think there'll just be too much systematic calibration uncertainty in the line width and the line spread function to measure the Doppler broadening. But I think the line center, I think you'll be able to measure pretty well, given enough counts and enough exposure time. And so that's probably something that's worth simulating, just how well you can track the center of that line, and that will give you the bulk motion, if there is bulk motion especially if there's different bulk motion as a function of azimuth. And you're absolutely right. That's you know, I've been thinking more about measuring the thermodynamic profiles out to R200 for these clusters. But Xtend might have something interesting to say about the velocity structure, especially when you are spending hundreds of kiloseconds staring at a few different clusters. That's a lot of data.
Mm-hmm.
Yeah. So yeah. So imagine what you can do with something like Suzaku or XMM at 6 keV in terms of the using the velocity structure, and you should be able to do that pretty well with Xtend too.
Okay.
So I don't have numbers, but that's something interesting to simulate. So if I have some time, maybe I'll think about that. You can also do it. Actually, I should point out that the response files are available for both of these instruments. If you email me, I'll tell you where they are. But if you just go on Google and search for the XRISM X-ray observatory, there should be a link to a page at ISAS in Japan, and that should have response files you can use to do simulations.
Okay, great. Thanks. So Rebecca?
Hi, can you hear me well?
Yeah, sure.
Okay, great. So yeah, that was one of my questions also, like if both instruments are going observed simultaneously. Well, anyway, one of my questions is actually about the ICM motion. And I was thinking if the XRISM instruments can tell apart a spectral line that was Doppler shifted by a line that is exactly from the same spectral central energy, So how is it? How the instrument is able to do this?
So it can. So your question is, if you imagine you have an emission line, and here I'll go to this spectrum. I think this probably tells it. So imagine you have an emission line that's at rest from some object, and the same object or some other material is emitting an emission line that's Doppler shifted. So you end up with two lines. So it obviously depends on what the relative velocity is. So if the velocity is too low, then those lines will just be blended, and it will just look like a broader line. But if the velocity difference is high enough, you should be able to differentiate both of those lines. And in fact, that is something that we hope to do in some clusters of galaxies. So what I didn't get a chance to talk about is, again, the Virgo cluster. And in Virgo cluster, this is a combined X-ray and radio image. The things shown in blue are X-ray, and you have these really bright radio lobes. And at the center, you have this supermassive black hole. This is actually the one that was imaged by the Event Horizon telescope, showing imaging the event horizon of a black hole for the first time. And all of this lobe structure tells you that the AGN is just really heavily feeding back energy and material into the local ICM, and it's producing these big radio plumes. It's also producing these plumes of X-ray emitting gas. What's interesting here, though, is that the dark blue that you can see all around, that's about 2 keV gas. This light blue, white, kind of whitish stuff is gas at 1 keV, and this was observed with Chandra. So even Chandra could tell that there kind of is this 2 temperature gas. So what we want to do with XRISM is to look at one of these arms which has this gas, and first of all try to distinguish the temperature between the cool gas and this 2 keV just general ICM, but also tell the difference in the velocity between the two of those, because we think this cooler gas has been uplifted by these radio emitting lobes, and probably is mixing metals into the ICM in this region. And so this is a simulated XRISM resolve spectrum. This was done by Aurora and Ionescu. And the black points show the total spectrum, but it's composed of 2 different parts. One shown in orange is this cooler 1 keV gas, and one shown in purple is the hotter 2 keV gas. And then if you just add them up, you get what's shown as the spectrum. And so you can sort of see that in some places, they produce the same emission lines, and so those just sum up. But in here, for example, and I can't really zoom into it, but this iron 2021 line, you can see that the hot gas produces this line, but the cool gas in orange does not. It's just not hot enough to produce it. And so being able to detect this line and then being able to separate it from this line right next to it is really key to being able to measure both the hot and the cold gas. And then you can imagine that if one of these components, one of these components has motion relative to the other, then that's going to shift the entire spectrum. So imagine that the purple component, or I guess, imagine the cool gas is moving at 200 kilometers per second relative to the ambient gas. Then that would shift this orange to the left by 200 kilometers per second. And 200 kilometers per second at 1 keV is, I'm not exactly sure what that is, but I think that's a keV or something like that. A little bit less than a keV, or sorry, an EV or something like that, a little bit less than EV. But even an even 1 electron volt of Doppler shift, the XRISM should be able to detect that. That's kind of at the limit, but it depends on the knowledge of the gain, so the knowledge of the energy scale, basically, how to convert the instrumental value for energy to actual energy. But that's expected, on Hitomi, that was something like 0.2 EV. And so a 1 EV shift would be 5 times that. So that's a 5 sigma result. And so, we should be able to detect just from relative Doppler shift, the motions of gas down to 100 kilometers per second, or maybe 200 kilometers per second. And that's well within what is expected for this. As I've mentioned, that's a lot less than the sound speed. So you imagine these plumes have to be moving at hundreds of kilometers per second. And so in the line of sight, we certainly expect to see that. But that's the way you would do that, just by, you do have to disentangle all of these components that add to it. And so it is a bit of modeling work to do this. But in theory, it's definitely possible just by looking at relative Doppler shift of the lines.
Yeah, that's what I was trying to figure out in my mind. Yeah. So you should you should know a priori on how multi-gas phase behave, right, in this whatever object you are looking at.
That's right. And that's actually hard to do because you don't really know that a priori. You have to get that information from the same observations. Because Chandra told us a little bit about the temperature of the gas, but these were grating observations. And so imagine all of this emission is kind of smeared out in a dispersion grating. And so you don't get very good spectral resolution even from a grating. So all of these lines are kind of mushed together. So you don't have this detailed spectrum already. So you'll have to get this from XRISM, and you'll have to kind of simultaneously fit the temperature components along with the velocity components. So we don't know what to expect, to be honest with you. It could be a really simple thing. We could just look at the spectrum and say, oh yes, this is exactly what's happening. Or there could be, a number of different velocity components and more than 2 temperature components. And then you have to do somewhat more complicated data analysis, but it's, it's still possible to learn something about this, and I expect that we will.
Yeah, sure. Thank you. Yeah. I have another question, if I can make it now.
Yeah, fine with me.
Okay. So if you can comment more on how these measurements, because you have higher spectral resolution now, and how XRISM would be able to constrain the supernova models. So my question is, especially is if there is an expectation to measure manganese, because manganese in particular is a really a super solar manganese over iron is especially good to tell apart the near Chandrasekhar scenarios and sub-Chandrasekhar scenarios.
Yeah, so that is a really exciting thing. So even in this original Perseus spectrum, you can see that the iron line obviously is really strong, but we have these other emission lines. Now, so here is, for instance, is the manganese line. Now, you can It's very faint. You can decide for yourself whether there's a real line there. The chromium line certainly seems to be there. I think the manganese line is probably a 2.5 or 3 sigma detection. But the fact that there's a little bump exactly where we expect manganese, I think also means there's something there. But you know, a longer observation, you'll be able to detect this line. And that, if I go way to the end, I do have a slide which explains this, because this was information we were able to get out even from Hitomi about the relative importance of different supernovae. So I didn't show. I showed this. I didn't show this. This is from a paper which I don't have a reference to, but I believe this was either an APJ letter. This might have been a Nature paper too. And this is from that same Perseus observation. And so we were able to measure the chromium abundance from that line. We were able to measure the manganese abundance from that line, although you see the error bars are a little big. And we were able to measure the nickel abundance from that same spectrum. The errors are definitely lower on nickel because it was a stronger line. All of these are with respect to iron, which we were able to measure very accurately. And this is exactly what you were saying. So there are different predictions on what these abundance ratios should be based on what the formation mechanisms are or for type 1a supernovae. Okay, this is not exactly my field. I'll point that out right now. But if you have, for instance, if the objects that are producing the bulk of type 1a supernovae are objects that are near the Chandrasekhar mass only, you expect to get a abundance ratio somewhere in this blue region. If they're all sub-Chandrasekhar mass, meaning that they're not degenerate, you expect to get them here. If you have a 1-to-1 mix of degenerate, so Chandrasekhar mass or and non-degenerate objects, you get what's in this red. So we've essentially ruled out that these are sub-Chandrasekhar mass objects that are producing supernova type 1. And it's much more likely that they are either single degenerate or double degenerate progenitors to type 1a supernovae. And of course, all of this comes from the abundance pattern that is left over in the hot gas in the cluster. So you're not observing the supernova or supernova remnant directly. You're observing the enrichment pattern that's been in place from lots and lots of supernova type 1 going off. But this is only, as I mentioned, this is only based on that one observation, which was fairly modest. So additional observations of Perseus and other clusters will put really good constraints on this, I think. And then you can start also to measure the abundance ratios as a function of radius out from the cluster, which would be very interesting too.
Yeah, thank you.
Sure.
One more thing, if you can comment on the missing pixel of the...
Oh, yeah, sure. I can. So let me go back to... Let me go back to a picture of the detector. So there are actually 36 pixels. I did not lie about that. There are a lot of slides, but I know there's a picture of the detector somewhere. Maybe very early. There it is. Okay, actually, I'm going to. Can you still see my screen? No, I don't think so. Sorry about that. This is easier if I do this.
Yes, now
Now
yeah.
I can, yeah.
Okay. All right. So this is the detector. There are 36 pixels here. Notice there are actually also 2 pixels down here. And these pixels are, when they're actually installed in the instrument, they're covered by a plate, so they're not exposed to the sky. And that plate has radioactive iron 55 on it, which produces manganese K alpha and manganese K beta lines. And so these pixels are used as calibration pixels. So they're always illuminated by these 6 keV emission lines. And the idea here then is that you know the energy of those emission lines that are constantly illuminating these pixels, And so you can follow as a function of time whether the signal from the detector changes, because you know it should always be the same because it's always the same energy. But there is, there is drift in what's called the gain or the energy scale of the instrument. And so the electronics, however, can only read the output from 36 pixels. So what they do in practice is they turn off one of the pixels in the imaging area so they can turn on one of the pixels, one of the calibration pixels. So that's why there's always a chunk missing, because they always have this calibration pixel being read out. And so they have to eliminate one of the pixels from being read out from the detector array. That's why there's always a gap, and that's why we always say there's 35 pixels.
Okay, thank you. Thank you so much for your talk. It was very interesting. Yeah.
My pleasure.
Okay. Thanks, Eric. So I don't see any more hands, and I think we are really past the time. And,
like a whole
thank you
second
very
talk.
much for being tortured here.
Oh, my pleasure.
It's kind of exciting and new.
Yeah, it is. It certainly is, and definitely start thinking about things you want to do. I think you'll all have an opportunity to propose for time, and hopefully XRISM will launch successfully very soon, and stay healthy and working for several years.
Okay. So again, thank you very much, and I hope you can come here to or there or where Rio is or the one is physically once the pandemic is gone.
Yeah, I hope so too. Be nice to see you all again.
Thank you very much, Eric.
All right, great. Thank you.
Thank you. Bye-bye.
Bye-bye.